In 2022, within the very first few months of operation, the James Webb Space Telescope started photographing something that appears nowhere in any prediction, any model, or any simulation astronomers had built before it launched. Small, faint, strangely red points of light scattered across the deepest images of the early universe Webb had ever captured. Nobody had a name for them yet. Nobody had a theory ready to explain them. They simply weren't supposed to be there, and there were far too many of them to dismiss as noise or error. Astronomers eventually gave them a purely descriptive name because nobody could agree on what they actually were. They called them little red dots. And 4 years later, some of the world's leading astronomers are only just now starting to figure out what they might actually be. This is the real story of one of the strangest open mysteries in modern astronomy, a population of objects that quite literally weren't supposed to exist, using nothing but genuine peer-reviewed research from the scientists actually studying them, right up through findings published only weeks before this video. Let's start with exactly what made these objects so immediately strange the moment Webb's first deep field images came back. Nearly as soon as the telescope began its earliest observation campaigns, astronomers noticed an unusually large number of small, compact, unusually red sources scattered throughout Webb's deepest images, appearing at distances corresponding to some of the earliest chapters of the universe's entire history. What made them so puzzling wasn't simply that they were far away. Webb was specifically built to find extremely distant, extremely early objects, using an infrared sensitive design specifically chosen, because light from the most distant reaches of the universe gets stretched into infrared wavelengths by the time it reaches us. What made them strange was how many of them there were, and how unexpectedly red and compact they appeared, properties that didn't cleanly match any category of object astronomers already understood. They were too small and too faint to obviously be full galaxies in the traditional sense, yet too red and too luminous to easily explain as anything else astronomers had catalogued before. In some of Webb's deep field surveys, these objects turned up in genuinely surprising numbers, dense enough that researchers quickly realized they were looking at a real distinct population rather than a handful of unusual one-off objects. Whatever they actually were, there were enough of them showing up across Webb's images that they couldn't simply be written off as a handful of unusual outliers or instrument artifacts. They represented a genuine, previously unknown population of objects, hiding in plain sight in some of the very first images this telescope ever captured. This single, unresolved mystery is closely tied to a much broader problem that emerged around the same time, one astronomers now generally refer to as the impossible galaxies problem. In February of 2023, a team led by Joel Leja, an assistant professor of astronomy and astrophysics at Penn State, published a study in the journal Nature, examining a set of galaxies visible in Webb's very first deep field images. What they found genuinely shocked the researchers involved. These galaxies existed only about 500 to 700 million years after the Big Bang, an almost unimaginably early point in cosmic history, a mere 3% of the universe's current age. Based on decades of established theory, astronomers expected galaxies from this era to be young, small, and blue, the natural color of freshly formed young hot stars that had only just begun burning through their fuel. Older stars, by contrast, glow with a redder light as they burn through their fuel and gradually cool over billions of years, which is exactly why finding red, aged starlight this early in cosmic history was so genuinely disorienting. Instead, several of these galaxies appeared to contain old, mature, reddish stars and were estimated to be roughly as massive as our own Milky Way galaxy, a galaxy that took over 13 billion years to reach its current size. Some of the galaxy candidates in Leja's sample appeared up to 50 times more massive than the roughly 1 billion solar masses astronomers had originally expected to find at this stage of cosmic history, an almost unbelievable discrepancy between prediction and observation. Leja described the reaction among his own research team plainly, saying they had looked into the very early universe for the first time with no idea what they were going to find, and that what they actually found was so unexpected it created genuine problems for existing science, calling the entire established picture of early galaxy formation into direct question. Now, it's important to understand that these enormous, unexpectedly massive early galaxies and the smaller, compact little red dots are related but distinct puzzles. Different pieces of the same broader pattern of an early universe that seems to have matured and organized itself far faster than any model predicted it could. And in the years since Webb first revealed both of these mysteries, astronomers have been working methodically, patiently, through an enormous amount of new data, trying to figure out exactly what's actually going on. That brings us to some of the most recent, most promising research specifically focused on solving the little red dots mystery, published only weeks ago as I'm putting this video together. A team of astronomers led by Vasily Kokorev at the University of Texas at Austin managed to capture what's being described as the deepest, most detailed spectral observation ever taken of a single little red dot, a specific object cataloged as GLIMPS 1775. This particular observation happened almost by accident, a genuinely fortunate coincidence in how modern astronomy sometimes works. Webb was actually pointed at an enormous cluster of galaxies called Abell, S-tone 63. Examining that cluster for entirely separate reasons, when researchers realized that the sheer gravitational mass of that galaxy cluster was acting as a natural magnifying lens, a phenomenon astronomers call gravitational lensing, bending and amplifying the extremely faint light from GLIMPS 1775, which happened to sit almost directly behind it from our point of view. Gravitational lensing is one of the more elegant tricks modern astronomy has learned to exploit, a direct consequence of Einstein's general theory of relativity, which predicts that anything with enough mass, in this case an entire cluster of galaxies, actually bends the fabric of space itself, and light traveling through that bent space gets bent along with it. When a massive foreground object happens to line up almost perfectly between Earth and something much farther away and much fainter, that foreground mass can act almost like a cosmic magnifying glass, stretching, brightening, and sometimes even duplicating the image of whatever sits behind it. In this case, that lensing effect made GLIMPS 1775's light powerful enough that researchers were able to extract roughly 30 separate spectra, detailed breakdowns of light across many different wavelengths, giving them an observational depth. Roughly equivalent to hours upon hours of dedicated telescope time, all made possible by a lucky cosmic alignment nobody had specifically planned for when they pointed Webb at that patch of sky. What they found, spanning an extraordinary 40 separate spectral lines, the most detailed spectral view of a little red dot ever captured, gave strong support to a specific, previously proposed explanation that researchers have been calling the black hole star scenario, often abbreviated simply as BH star. Under this hypothesis, little red dots aren't galaxies in any conventional sense at all. They're something stranger, a supermassive black hole that's actively growing, densely wrapped in a thick, partially ionized cloud of surrounding gas, a structure compact and luminous enough that from a distance, and at these extreme distances, it can visually mimic the light signature of an entire young galaxy, despite actually being something dramatically smaller and more exotic. Think about what that actually implies. For years, astronomers studying these objects had been trying to understand them using the same tools and assumptions they'd normally apply to galaxies, counting stars, estimating stellar masses, trying to work out star formation rates. If the black hole star scenario turns out to be correct, all of those earlier assumptions would need to be thrown out entirely for this specific population of objects, replaced with an entirely different physical picture centered on black hole growth rather than conventional galaxy assembly. Kokorev described the moment his team first examined this incredibly detailed spectrum as feeling like having every piece of a puzzle scattered across the floor. Researchers picked up each individual piece, carefully measured every spectral line, and slowly began fitting them together. And while a few pieces initially looked like nothing meaningful on their own, several of them eventually clicked into place, revealing that there really was a coherent, identifiable structure hiding inside the data. There's a reason this particular explanation, if confirmed, would matter enormously beyond just naming a strange category of object correctly. Astronomers have separately been struggling for years with a related puzzle, how supermassive black holes, some containing the mass of millions, or even billions of suns, managed to grow so large so quickly in the early universe within time frames that standard black hole growth models struggle to explain. If little red dots really do turn out to be actively feeding supermassive black holes, wrapped in dense cocoons of surrounding gas, then this strange, previously unrecognized population might represent exactly the missing evolutionary stage astronomers have been searching for, a kind of transitional phase capturing these black holes in the act of rapid early growth, hidden inside gas clouds, dense enough to have kept them disguised as ordinary galaxies until Webb finally had the sensitivity to look closely enough to tell the difference. In other words, solving the little red dots mystery wouldn't just answer one isolated question. It could potentially unlock a much bigger, long-standing puzzle about how the universe's earliest, most massive black holes actually came to exist in the first place. There was one specific complication in that data worth understanding, because it shows just how carefully this kind of research actually has to be conducted. Part of GLIMPS 1775's spectrum was initially missing a specific feature scientists expected to see if the black hole star hypothesis were correct. Something called a Balmer break, a particular dip in light emission that serves as a kind of chemical fingerprint for this type of object, caused by hydrogen atoms absorbing light at a very specific wavelength. Its presence or absence tells astronomers a great deal about the physical conditions inside whatever object they're observing, which is exactly why its apparent absence here was initially concerning for the team's leading theory. Rather than treating that missing piece as evidence against their theory, or worse, quietly ignoring the inconvenient gap in the data, the research team brought in supplementary observations from the Hubble Space Telescope, and that additional data resolved the apparent contradiction entirely, revealing that interference from a separate, much larger host, galaxy sitting along the same line of sight, had simply been obscuring that particular signal, essentially hiding it behind an unrelated foreground light source rather than indicating anything wrong with the underlying theory. Kokorev summarized the outcome with visible relief, saying that everything fit, nothing was broken, and that it actually made the puzzle of the universe even more satisfying to finally understand. It's worth being honest about exactly where this research currently stands, because good science doesn't claim more certainty than the evidence actually supports. This new observation offers strong, genuinely compelling support for the black hole star explanation of little red dots, but Kokorev himself was careful to note that other interesting theories are still being seriously proposed and investigated by other research teams. While the black hole scenario is very much the leading candidate at this point, he suggested that a fully confirmed answer might still be a year or two away, as more of these objects get studied with the same level of detail across different regions of the sky. So here's what I actually want you to take away from all of this. 4 years ago, James Webb photographed something that fit into absolutely no existing category of object astronomers understood, scattered across some of the earliest, most distant images of the universe ever captured. For years, nobody could say with real confidence what these little red dots actually were. And only within the past few weeks, through an incredibly fortunate cosmic alignment and some of the most detailed spectral analysis ever performed on a single one of these objects, astronomers finally have their strongest evidence yet that they might be looking at something genuinely new to science, actively growing supermassive black holes wrapped in dense cocoons of gas, mimicking the appearance of galaxies from a period in cosmic history when nothing like them was supposed to exist at all. That's not a closed case. It's an active, ongoing scientific investigation, playing out in real time, with new evidence still arriving and real uncertainty still on the table. And that's genuinely the more interesting version of this story anyway. It would be easy to tell you that scientists have definitively solved the mystery of little red dots, wrap this up with a tidy bow and move on. But the honest version is messier and more human than that. A small team of researchers getting an incredibly lucky observational break, spending months carefully checking their own data against every possible alternative explanation, resolving an apparent contradiction rather than sweeping it under the rug. And still, even after all of that careful work, describing their own conclusion as strong evidence rather than absolute proof. That's what real astronomy actually looks like, and I think it's worth appreciating exactly as it is. If you want to know the moment scientists finally confirm exactly what little red dots actually are, subscribe and turn on notifications, because Kokorev himself says that answer could arrive within the next year or two, and we'll be covering it to the moment real. Published research settles the question. And drop a comment telling me whether you think these mysterious objects turn out to be black holes wrapped in gas, some entirely new category of early galaxy, or something nobody has proposed yet, because after everything James Webb has already shown us, I genuinely wouldn't bet against one more surprise.